Hey folks, in this last part of the unit we have two videos on orbital motion. We'll start out with a definition and move on to one of the laws of orbital motion in the next video. So we are talking about satellites. Satellites are any object orbiting a larger object in the solar system or universe. The Earth is one of the Sun's satellites. We're going to focus more on satellites of Earth, mostly because the smaller the orbit, the more circular it gets. So any satellite that a human has put into orbit around Earth has a pretty much circular orbit. Even something like the moon, that's a lot further away, has a nearly circular orbit. So we can approximate everything as a circle for our purposes here. From what we know about circular motion, this satellite that is orbiting the planet has a velocity that's directed always tangent to the circle, and it's changing directions even though the speed is the same. And then there's an acceleration that is centripetal, so it's directed toward the center of the planet. That centripetal acceleration has to be caused by some number of forces. If I were to think about the forces acting on this satellite, well, there's nothing propelling this satellite. Once it's set into orbit, there might be some minor corrections that need to happen using some thrusters, but there's nothing happening otherwise. It's just hurtling through space around the planet. That means that the only force that could be acting on this satellite is gravity. So if you were wondering why astronauts who are on the International Space Station experience zero gravity, it's not that they experience zero gravity. It's because the only force acting on the International Space Station is gravity, which actually qualifies the International Space Station as something in free fall. So that space station and any satellite is essentially a projectile that just never lands. And so the astronauts don't feel gravity because they are falling with the same acceleration as the entire space station, and so they can move around freely. That's how they do like zero gravity flights. They like take a plane way up high in the atmosphere, and then it just like dives for a while, and everyone inside experiences zero gravity. Anyway, we're here to analyze the orbital motion of a satellite due to this force. So this net force will be centripetal, and so will the acceleration be. The net force is caused by gravity. Now, this satellite is pretty far away from the surface of the Earth, so we're going to use the bigger gravitation equation. And we're going to say that the net centripetal force is equal to the force of gravity, G big M little m over r squared. And that is equal to mv squared over r. One of the masses cancels. Now, we have a free body diagram that is for the satellite. That means that the satellite's mass has to be little m in this case. So little m cancels. The planet over here has mass of big M, and so that mass doesn't cancel. The other thing that happens here is I have r squared in this denominator and r in the other denominator, so I can multiply both sides by r and do some more canceling. I'm left with, I'm going to slide over here, gm over r equals v squared. And if I solve that for v, I get a very important equation for orbital motion. I get the orbital speed of a satellite. It is equal to the square root of big G, big M over R. Okay. I actually haven't checked to see if this is on your equation sheet. I kind of doubt it is, but they added some equations, so it might be there. So this is the speed that a satellite needs to have to maintain an orbit of radius r around a planet of mass m. So let's make some notes about this. This capital M is the planet mass. That's really important. So the mass of the planet determines how fast you have to go. You can see a direct relationship there. The heavier the planet, the faster the satellite has to go at a particular radius. Speaking of the radius, that r, if you look at the picture, r goes from the center of the planet all the way to the satellite. That is the planet radius plus the altitude of the satellite. So that's a question that comes up a lot for orbital motion on the AP exam, is like making sure that you understand that this value of r is not the radius of the planet. It is the distance from the center of the planet to the satellite itself. This last thing I want to point out is the one that I always found surprising, is this proportionality. The speed of an orbit is proportional to the square root of 1 over r. And that struck me as strange, right? Like, as the radius of orbit increases, the required speed to maintain that orbit decreases. So the further away a satellite gets from its planet, the slower it needs to go to maintain an orbit. And I find that interesting. So I just want to do one problem with this equation, and I kind of messed up writing it, so I'm going to have to clarify. A satellite with mass m orbits at a distance r from the center of Earth and has a speed v. In terms of v, what is the speed of a satellite with mass 2m orbiting at a distance of 4r? So I'm going to start with this, and I'm going to do a clarification here. I'm going to call this mass me, so that's the mass of the Earth. The mass of the satellite is m. I used capital M. And so right away I'm going to eliminate those, because if I change the satellite's mass, this equation tells me that that will not affect the required speed of orbit. All right, what will affect that speed is the radius. Maybe now you've seen enough of these, so you want to like pause the video and try and do this in your head. So I'm just going to fix that. So the initial orbital radius was capital R. The new orbital radius is 4r. And so I want to figure out what that is in terms of the original. So I will extract this 4, which means I have to extract 1/4. I need a numerator and a denominator. So the square root of 1/4 times the square root of gm over r. Gm over r, square root of gm e over r is the original v, and then the square root of 1/4 is 1/2. So this new orbital speed is 1/2 the old one. So if I quadruple the orbital radius of a satellite, I only need to cut the orbital speed in half to manage that orbit. There's a lot more here that can be talked about, but in this course, that is the long and the short of it. We might talk about more of it during class because it's cool, but that's it for now.